was left to do was to do the partial with respect to z branch. What is the partial of this function with respect to z?
Negative xy sine yz.
Now look at that new function. Take its partial with respect to x. Partial with respect to x of that new function.
Negative y sine yz.
So go back to that partial. Take its partial now with respect to y. What is it?
That's what I had to. Negative xc cosine y sine.
So you're looking at this one here, right? So partial of that with respect to y. Remember, that is a product rule. Now, what is that partial with respect to z?
Negative xy squared cosine y sine.
So that is all 9 second order mixed partials. No, not just mixed, just all 9 second order partials. X, Y, Y, X, are they the same? Yes. There's XZ. ZX, were they the same? And then YZ, ZY, are they the same? Good. As they should be. All right, So you have 3 pairs that are identical, so you actually only have 6 distinct second order partials. Again, that is Claret's theorem. I think that's how it's spelled. Go ahead and double check that spelling. No, that is not its spelling. There should be an A. Clairaut's theorem. So close. This is not the actual theorem, I'm just kind of paraphrasing it. Laplace's equation. So this is a 2-variant Laplace's equation. I think we actually will relook at Laplace's equation, maybe. We haven't actually looked at this operator yet. But that is the actual equation. I think we use what, U? But we'll study that operator. Want to determine which of these 3 functions, if any, is a solution to Laplace. So here, let's just focus on Z1 first. It's partial with respect to x. Second order partial with respect to x. Partial with respect to y. What is it? Still looking at Z1. Second order partial with respect to y. It's a solution. By the way, such an equation, so Laplace's equation, a partial differential equation. Sadly, methods of solving partial differential equations not as easy as ordinary. Let's focus on the Z2 now. Partial with respect to x. What is it? Half. Second order partial with respect to x. Partial with respect to y. Second order with respect to y.
1/2
Their sum is just e to the x plus y, which in fact never would be 0. Not a solution. Now let's examine the Z3. Partial with respect to x.
2x minus y squared.
It's just 2x. Second order partial with respect to x. What is it? You said
2.
it's positive 2. Yeah, that's partial with respect to y.
-2.
And second order with respect to y.
-2.
It's -2. 2 plus negative 2 is 0. That's a solution. So Z1, Z3 are the solutions, Z2 is not a solution. Moving along. Schedule. Tangent plane. And so we had the concept of a tangent line, right? That is to a curve. Well, if we're given a surface, three-dimensional, at a point, we can have a plane that is tangent to the surface. You can also still have a tangent line. Now we're going to look at the tangent plane. So the point x0, y0, z0. Point on the surface of S. Let's see be any curve that is tangent, or I'm sorry, any curve passing through P0 that lies entirely in S. The tangent lines to all such curves at that point lie in the tangent plane. And so that's the definition of the tangent plane. It's the collection of all those tangent lines. Easy way to find the equation. Surface is defined by the function f of xy. Equation of the tangent plane at the point P0. Z equals f of x0, y0 plus the partial of f with respect to x evaluated at x0, y0 times x minus x0. Then plus the partial of f with respect to y evaluated at x0, y0 times y minus y0. just like single variate functions y equals f of x, you have a differential for y. You also have a differential for a multivariate function. Say z equals f of xy, or f of x1, y, or x1, x2, x3, or any number of variables. We call this now the total differential. And it's the sum of the partial of f with respect to each independent variable times the differential for that variable. Chain rules. Let's say both x and y are functions of t, and z is f of x comma y. Right. Both x and y are differentiable in t, f is differentiable of x and y, then z is a differentiable function of t, and that needs to be fixed. Okay. There we go. dz dt is partial z partial x times dx dt plus partial z partial y times dy dt. Now let's suppose that x and y are functions of u and v. Again, let z be a function of x and y. Right? If both x and y are differentiable in u and v, z is differentiable in x and y, then z is also differentiable in u and v. And partial z partial u, partial z partial x times partial x partial u, plus partial z partial y times partial y partial u, and partial z partial v, partial z partial x times partial x partial v, plus partial z partial y times partial y partial v. in general, W is a function of m independent variables, x1 through xm. Each of those independent variables is itself a function of n independent variables, t1 through tn. Then W would be a differentiable function of each of those t sub i's. And the partial W with respect to t sub j is the sum, I equals 1 to m, of partial W partial xi times partial xi partial tj. Go back to Calc 1. Who remembers that? An implicitly defined curve. So circle would be implicitly defined. It's x squared plus y squared equals r squared. Remember doing implicit differentiation back in Calc 1? Remember how much of a pain it was? Can we have implicitly defined multivariate functions? Uh-huh. So we'd also have implicit differentiation for multivariate as well, right? Oh, that sucks. Oh, except we have chain rules now. Multivariate chain rules. So we can make this process a lot easier. First, revisit the two-variate implicit. So say that f of xy defines y implicitly as a function of x via the equation f of xy equals 0. Then dy dx is partial f partial x, a negative partial x over partial f partial y. Provided partial f partial y is not 0. Oh, that just made the process a lot simpler. No more algebra.
Why is it y that's getting defined implicitly?
Doesn't have to be. We're just saying here y is implicitly a function of x, so we can write dy dx. you just flip it if it's dx dy. Well, then you'd have similar things. If f of x, y, z equals 0, define z implicitly as functions of x and y. Right, then implicit differentiation, partial z, partial x, negative partial x over partial f, partial z. And then partial z, partial y is negative partial f, partial y over partial f, partial z. Could you still use the Calc 1 technique? Yes. Right, so you could still just go turn by turn using your chain rules and then algebraically solve for, let's just say, the partial z, partial x. You can still do that. Of course, that process takes a lot longer. Another spam text. Total differential. So the first thing you want to determine, z is a function of how many variables? 2, right? So we're going to have 2 terms in our sum. That is going to wind up being our total differential. Partial of z with respect to x. What was it? Now partial z, partial y. And there's your total differential. These differentials have the same applications as they did in Calc 1. As linear approximations. That's the first term. Hmm? Well, not D, partial. Which is what?
Sine y.
Hmm?
Sine y. Minus y cosine x.
Second term. Don't get the dy, and there's the total differential. Let f of x, y, z be a differentiable function. We want to evaluate partial f, partial rho, partial f, partial theta, and partial f, partial phi. Rho, theta, and phi. What does that make you think of? Spherical coordinate system. X, y, and z would all be functions of rho, theta, phi, right? What is x? What is it? Rho. Yes, I did hear you call it P, by the way. I was giving you a chance to redeem yourself. Is that it?
Sine phi.
What about y?
Rho sine phi sine theta.
And what is z?
Rho cosine phi.
Keep those in the back of your mind. Here's a question. Do I want to write it in the partial notation or the subscript notation? Subscript. Partial of f with respect to rho. Using chain rule. partial of f with respect to x times partial of x with respect to rho plus partial of f with respect to y times partial of y with respect to rho plus partial of f with respect to z times partial of z with respect to rho. What is the partial of f with respect to x? It's a gotcha question. It's just partial of f with respect to x. We don't know what f actually is. So it stays as partial f, partial x. What is the partial of x with respect to rho, though?
Cosine theta sine phi.
Partial of f with respect to y.
F of y.
It's just partial of f with respect to y. We don't know what f is yet. What is partial y with respect to rho? And then partial of f with respect to z.
Cosine of theta.
And partial of z with respect to rho. So if I just write it out now using the partial notation, because that's what the problem asked for. There it is. With respect to theta, So again, those partial f's are all going to remain the same. What is the partial of x with respect to theta? Negative rho. What is the partial of y with respect to theta? What about the partial of z with respect to theta?
That's what the cosine theta.
What is it? It's just 0.
Why is it 0? Because z doesn't have theta.
So rho and phi are constant. So that's just a constant that you're differentiating. And there's your formula for partial f, partial theta. Now with respect to phi. Partial x, partial phi.
Rho cosine theta. Cosine.
Y.
It's rho sine theta. Cosine theta.
Oops. And finally z.
Net.
Go away, curly pilots. Now be your formula for partial f, partial phi. So what we just did is found the formulas for the partial of a rectangular function in spherical coordinates. I'll let you derive the formulas in cylindrical. And so every given rectangular function, find its partials in cylindrical. U is x squared plus 2y squared plus 2z squared. We're going to use the results that we just came up with to find u rho, u theta, and u phi. Well, what's u sub x?
It's
Just 2x, right? What is u sub y? And u sub z? Well, that's a nice function. U rho, if we look here, cosine theta sine phi times u sub x plus sine theta sine phi times u sub y plus cosine phi times u sub z, right? We can't leave it like that, though, can we?
because it has x, y, and z, which is rectangle.
So we're going to have to write this x, y, and z in terms of pure spherical. Well, that should be fairly simple. Is there any way to simplify that? Hmm? You could. What benefit will that serve? And what were you saying? You can't. If that was a 4-row in front, you could. But sadly, it's not. Then we could try to use some reduction formulas on cosine squared and sine squared. Is it really going to simplify it? No. So just leave it. few thetas next. There's what we're looking at, right? There's negative rho. Sine theta sine phi times ux plus rho cosine theta sine phi times ui. Do it on the line. X is rho cosine theta sine phi. Can that be simplified? How's it simplified? What is it? I wouldn't factor anything out yet. So they can actually be combined, which is nice. Is that fully simplified? Give you a hint. Hmm? What is it? Just sine times cosine is sine of 2 theta? 2 sine theta cosine theta is double angle for sine. Rho squared sine of 2 theta sine squared of phi. I would say that is definitely simpler.
In the initial question, where did you get the cosine theta from that you added to the
Which cosine theta?
I guess for the x component where it's negative 2 rho sine theta cosine theta.
Here?
Yeah.
What's x in spherical coordinates? Rho cosine theta sine phi. Right, so that's where that extra cosine came out of. Right, now this is what we're looking at. Two x then plus rho sine theta cosine phi times the 4y minus rho sine phi times the 4z, right? Now evaluate x, y, and z in spherical. Can we simplify that? So, kind of have time, so let's just do this. Each of them has a 2 cosine phi sine phi, which is double angle on sine. Factor out a rho squared sine of 2 phi. Sine squared minus 1 is negative cosine squared. So this here is just negative 2. Or negative 2 cosine squared, rather. That would be fully simplified. Negative rho squared cosine squared theta sine of 2 phi. So I forgot that there are actually 2 assignments for multivariate functions. There was multivariate functions and then one on just limits. I have changed the due date for homework 11 to be to tomorrow. It was originally today. So both 11 and 12 will be due tomorrow. That is multivariate functions. 13 is then on partial derivatives. 14 and 15 are tangent planes and chain rules. One is for chain rule, one is for tangent plane. I don't remember which one is which, though. They will be due next Friday, the 14th. Also, your project is due next Friday. We will finish up tomorrow. See that?